Welcome to this presentation. This work is titled Trace Checking of Cyber-Physical System Properties, Bridging the Cyber-Physical Gap. This work was done in collaboration with Enrico Vigano, Domenico Bianculli, and Lionel Brian. We did this work with LuxSpace, a space system integrator based in Luxembourg. Specifically, this work is focused on the Israel satellite. The main goal of Israel is to collect tracking information from vessels operating on Earth. This is a representative case study that contains problems that are common for the development of cyber-physical systems. Our high-level goal is to support engineers in the verification and validation of cyber-physical systems. For example, Israel has to satisfy many requirements. One is reported in these slides and says that whenever the satellite mode switches from idle mode to normal mode, the angular rate shall reach a value lower than 1.5 degrees per second within 10 seconds. Moreover, the angular rate shall stabilize around an arbitrary value c lower than or equal to 1.5 degrees per second. To verify that the system does not violate this requirement, engineers analyze traces coming from the system. For example, a fragment of an execution trace of Israel is reported in this slide. The trace reports on how the angular rate and the mode of the satellite change over time. The timestamp value contains the time instance at which the values of the angular rate and the mode of the satellite are recorded. The index value is an incremental index that contains the indexes of the different timestamps. After the engineers collected the trace, they check if the trace satisfies or violates the requirement. This activity is known as trace checking. The high-level goal of this work is to automate trace checking. Specifically, we will propose a framework that automatically checks whether the trace satisfies or violates the requirement. To be applicable and useful in practical domain, our trace checking framework should satisfy two goals. First, it should support a language that can express complex cyber-physical system requirements, that is, requirements that involve software and physical components. And second, our trace checking framework should apply to industrial execution traces. That is, it should provide results within practical time limits. Our contributions are as follows. First, we propose the hybrid logic of signals, a new language to express complex and industrial cyber-physical system requirements. Second, we propose ThEodorE, an efficient trace checking tool that can analyze requirements expressed using the hybrid logic of signals. We will discuss each of these contributions in the following. Let's start from the hybrid logic of signals. Let's consider the requirement we previously discussed, which is not expressible in existing languages for signal-based temporal properties. Let's identify the main features a language needs to express this requirement. Our language should be able to express constraints on the trace indexes. Specifically, to express that the satellite mode switches from idle mode to normal mode, we should specify that there exists an index such that the mode of the satellite is 0. The value 0 assigned to the variable mode specifies that the satellite is in idle mode. Additionally, we should specify that in the next index, the mode of the satellite is free. The value 3 assigned to the variable mode specifies that the satellite is in normal mode. In this case, the records with indexes 3 and 4 satisfies this property. Additionally, our language should be able to express constraints on the timestamps of the trace records. For example, to express that the angular rate shall reach a value lower than 1.5 degrees per second within 10 seconds, we should specify that there exists a timestamp such that the angular rate is lower than 1.5 degrees per second. For the trace reported in these slides, the record with timestamp 5.7 seconds satisfies this property, since the angular rate is 1.1. Additionally, we should specify that the difference between the timestamp 5.7 and the timestamps at which the mode of the satellite change is at most 10 seconds. Finally, our language should be able to quantify the values of real value variables, specifically to express that the angular rate shall stabilize around an arbitrary value c. We should specify that there exists a value c lower than or equal to 1.5 degrees per second, such that the angular rate stabilizes around that value. Our language hybrid logic of signals provides all these features. Due to time constraints, we use a portion of the previous requirements to describe the properties of this logic. The hybrid logic of signals allows using existential and universal quantifiers to quantify over the values assumed by timestamp variables, index variables, and real value variables. Additionally, the hybrid logic of signals supports specification that use the at timestamp operator, at t, to retrieve the signal value in a record with a given timestamp, the at index operator, at I, to retrieve the signal value in a record with a given index, to use the index to timestamps and the timestamp to index operators to retrieve the timestamp associated with an index and vice versa, to create expressions combining timestamps, indexes, and real value variables. ThEodorE is an efficient trace-checking tool that can analyze requirements expressed using the hybrid logic of signals. The main idea behind ThEodorE is to reduce the trace-checking problem to an SMT satisfiability problem. ThEodorE works in 3 steps. First, the trace to target logic component translates the trace into the input language of the SMT solver. Second, the property to target logic component translates the requirement into the input language of the SMT solver. Finally, the satisfiability checking component verifies whether the generated formula specified using the target logic is satisfiable or not. If the formula is satisfiable, the trace violates the requirement. Vice versa, if the formula is not satisfiable, the trace satisfies the requirement. Our evaluation assessed the main contributions of this work. We considered 2 research questions. In research question 1, we assessed to which extent the hybrid logic of signal can express requirements from industrial cyber-physical system applications. In research question 2, we assessed the applicability of ThEodorE, that is, whether ThEodorE can verify cyber-physical system requirements on industrial execution traces. To answer research question 1, we considered 212 industrial requirements from EZ. We compared the expressiveness of the hybrid logic of signal with the expressiveness of SBTEM-CDSL and signal temporal logic, which are 2 languages for expressing signal-based temporal properties. Our results show that the hybrid logic of signal could express all the requirements of our case study, many more than SBTEM-CDSL and signal temporal logic. To answer research question 2, we consider 747 trace requirements combination. We compare the applicability of ThEodorE with SBTEM-CCheck and BReach, which respectively support the hybrid logic of signal, SBTEM-CDSL, and signal temporal logic. Our results show that ThEodorE computed a verdict for 74.5% of the trace requirements combinations we considered. For 25.5% of the trace requirements combination, no results was provided. This was caused by the limitations of the underlying SMT technology. We also consider 337 trace requirements combination that could not be checked by the other 2 tools, since the requirements were not expressible in SBTEM-CDSL and signal temporal logic. For this trace requirements combination, ThEodorE produced a verdict for 67.9% of the cases. Let's now discuss our conclusions. The high-level goal of this work was to support engineers in the verification and validation of cyber-physical systems. For this reason, we proposed the hybrid logic of signals, a language to express complex and industrial cyber-physical system requirements. We also proposed ThEodorE, an efficient trace-checking tool that can analyze requirements that are expressed using the hybrid logic of signals. Our evaluation showed that the hybrid logic of signals was able to express all the cyber-physical system requirements of our case study. The hybrid logic of signals supported a much wider set of properties than other existing languages. And finally, ThEodorE checked most of the requirements we consider within practical time limits. Thank you for your attention.
Hello, everyone. we are back here with Claudio, Lionel, and Enrico. Okay, and we would like to read your questions. So please don't hesitate. Go ahead, and yeah, it's been a really cool work. But probably there are things to ask as well. Okay. In the meantime, I'm going to start the conversation. So if you are inspired, please join us virtually. Okay. Stay silent. Who wants to answer? Sorry, I cannot read the. Grisha has made a question through the chat. So please go ahead and read it aloud if you wish.
Yeah. So Grisha asked, based on your experience with other cyber-physical system cases, how applicable is this framework in other domain like automotive? So in our work, we only applied our work over one case study, which is on the satellite domain with our industrial partner. However, we believe that this case study is sufficiently complex and representative of other domains. So we believe that our language and our trace checking approach can be used in other cyber physical system domains like automotive and others. Of course, I mean, more empirical study and more empirical assessment of our language and our framework are welcome. And we believe that this is definitely a part of our future research direction.
Yes, in another way to say it is that as long as you can express your properties in the hybrid logic of single language, then you can use it. It doesn't matter what the domain is, as long as you can express the properties in that language.
Yeah, that is correct. Domain independent. I also see it. Obviously, this is not my field of work, but I understand that you are, well, essentially, between quotes, that's not that essentially thing, adding temporal properties to essentially a linear temporal logic. This is how I understood it. Maybe I am mistaken.
Yeah, I mean, I must say that we took, I mean, just to add some comments of this, we took a different approach than what, for example, logicians do, which is usually they start with some logic and then they try to kind of use the logic in some domains. So we started with an analysis of our problem, by trying to analyze the needs of our industrial partner and see whether there were existing tools that we can reuse. So in some sense, our logic is a superset of existing logic because it can express properties that can express in signal temporal logic, which are, we call them time-based languages. On the other hand, or signal-based languages, we can also express properties that need you to predicate on indexes, like, for example, LTL, and as well as also again to quantify over variables, over generic variables.
There are two steps, let's say, in your proposal. The first step, the second step is clear to me. You take your language, an expression in the language that you have proposed, and then you transform it to a formula, logic formula that can be analyzed in SMT provers or analyzers. That's clear to me. And I confess that I haven't read the paper, so that's probably what it is unclear. But the first part, that is translating the traces into a formula, could you explain a little bit how it works? I mean, what is the idea? How do you translate a trace into a logic formula? What is the basis?
Yeah, so I mean, the main idea is to translate everything into a logic formula, so which is the trace plus the requirement. And the logic formula is expressed using the input language of the SMT solver. Now, we use a specific interface to Z3, which is called Z3 Pi, which essentially, as array, it offers you, I mean, actually also the encoding of Z3 allows you to use array, but essentially we encode the trace within a sequence within an array. And then, of course, we use the formulae to quantify over the elements of this array.
Understood. Understood. No, because I was thinking maybe I was influenced by the previous presentation, the first presentation of this session, that you maybe were inferring a model from the trace. The first talk, for instance, that we have this morning, they create a model, a logical, a state transition diagram on the basis of the trace. So for the translation could be done in different ways, creating a state transition model, create a right. That is the question, okay, the reason of the question. We have a question made by Michelle Chiari, okay? Yeah, that if you want to take a look at it.
Yeah, great. Okay, were the traces you analyze is in the evaluation taken from a simulation or were they real world? This is a tricky question because we got the traces from a scenario in which it's a real world. So they were simulating the physical satellites. So they were essentially, they have the physical satellites. Some parts actually were simulated. For some others, there were actually physical components. And then they essentially recorded the behavior of the satellite. So it's physical in the sense that the satellite was physical, but some of the components were actually simulated. So I would say it's hybrid scenario. But now we got actually the traces after the satellite is deployed. So the satellite was deployed in September, and now we have the traces of the actual satellite in space. So now we are kind of moving toward a fully, actually not real world, even deployed scenario.
Yes, SL is actually in space right now.
Yeah.
So it wasn't the case when we did the work, but it is the case now. But you know, it's pretty standard in CPS domains that you do a great deal of testing combining simulation and hardware in the loop on the ground before you deploy it. I mean, you know, it's a normal practice in CPS domains. Yeah.
And no, go ahead, Lionel. I started speaking.
No. What I mean is that simulation plays a very important role in all CPS domains, so that you can do extensive testing, including that kind of analysis before you deploy.
Yeah, imagine that now.
You cannot deploy and test. You cannot test on the deployment platform. In the real environment, it's not. You cannot do that, or at least that's the last stage.
I imagine that from a requirement perspective, once the satellite is in operation, there is little you can do. I mean, it's working.
There is acceptance testing even before it's put in operation, but it's very limited. So you need to do massive testing and analysis before you deploy.
No, but
simulation plays an important role. Yeah.
It is true that for mission critical systems, satellites, airplanes, etc., we need to face the problem from a different perspective. We cannot test the real, at least not as we test a piece of software. So we need to think otherwise. I mean, like as you said, maybe simulation, maybe small scale
Usually
analysis.
It's a mix of simulation and hardware in the loop usually.
Mm-hmm.
Depending on the circumstances, some instruments can be in the loop, actual instruments. But, go ahead,
Claudio, sorry.
Yeah, I was just saying that there is actually the physical satellite, and there are actually actuators that simulates. I mean, they act on the physical satellite, and they make the behavior of the satellite. They simulate the behavior of actually the space, including forces that act. So I would say it's a simulated environment, but there is a physical interactor, so it's real world.
Yes.
You have the key question in the chat.
Is
the tool available?
Yes, the tool is publicly available. What is not available, because we cannot release them due to the non-disclosure agreement, are the traces and the requirement. But the tool is available, yes.
Perfect. Sorry, guys, we need to stop here. 10 seconds to go to the discussion room. I encourage everyone to join the authors there. And thank you very much for being there.
Thank you.